Today we're going to do something a little bit different. We don't always do it, but it's really important, and it's a deep thing. We only have one lecture. You might not fully understand it, but you'll be ahead of the other people in the field who aren't even going to be exposed to this. And I mean, you've read the paper, I hope. The paper on options, and it's almost 20 years old, 18 years old, but it's been very influential, but still there's some large proportion of the field that hasn't really fully grokked what's in there, and it's kind of deep. So take your time and think about it. So the problem of temporal abstraction. It's a main way to get abstraction, because if you've been thinking about reinforcement learning, you've been thinking about Markov decision processes, it may strike you as sort of like a clockwork understanding of the world, where there are little steps, and it seems like the way we understand the world is maybe more larger than that, more sophisticated than that. And I think it is. I think we don't think about the world in terms of these tiny little steps, and we have higher level concepts. And so you may be thinking, well, I'm learning fine about reinforcement learning, I'm learning about AI, but it doesn't really capture these important larger things. And the conclusion that I wanted to sort of suggest to you is that maybe it does. Maybe it does if we include these the full set of possibilities with abstraction through options. Okay, so we want to go beyond the low level. We want to connect up the ideas you've learned about to the high level, to make them relevant. So the physical level to the human level, the action level to the decide level. Action level seems small. It's meant to seem small to you, like a little joint torque or a force applied to the mountain car. Whereas we in our lives, we don't make we do make decisions at that level. We do move our fingers or move our hands. If we have to make a phone call, we have to dial each digit. Actually, we don't dial anymore, do we? I guess we just push little buttons. We do have to push each little button. But then there's the bigger choice was to make this phone call rather than make another phone call, or to call this person rather than another person, and in our lives we have to make high-level decisions, like to take an airplane home, or to take a new job, or to go to school. Our planning, even to come here, you had to plan to be here at a certain time and to walk here, and these are all higher-level decisions. They're not well modeled by the low-level decisions of an MDP. Okay. So let's first acknowledge that there's a big mismatch between the kind of decisions that people make in their lives and the low-level decisions of the MDP. Now, it's common to take the MDP thing and apply it to large decisions. Like, I'm a company, I'm trying to decide, should I go into this market or should I not? And they might do research, try to estimate the probabilities for these big steps. But that's not really satisfactory to us, because we want to model like human performance, and humans are able to make small decisions. We simultaneously want to make small decisions and also have the ability to make large decisions. And so it seems like there's a mismatch. We'd have to go to like a 2-level system or something, and all that is just awkward and messy, and it will just get worse and worse as we go to more levels and have to try to interrelate them. So what I'm going to tell you about today is a way of having one level, and it's the low level, and yet we're also going to be able to think at a high level. Okay? And it's all done through an idea called options. We want to keep, as a bottom line here, we want to keep the elegance and clarity and simplicity of everything you've learned about in this course, and yet while connecting to and crossing up to the high level. Okay? So we want to extend the framework. It keeps all of our friends, keep value functions, keep planning, keep Bellman equations, keep the models. Everything will be just as you've known about. We will retain all of that, but we will extend to to larger things, okay? And so I'm saying it's a dimensional thing because we can keep everything you know is going to extend into this higher level actions that are overlaid on top of the low level actions. Okay? And as I said, the key concept, key mathematical concept, or key formal concept is that of an option. An option is a pair of a policy and a termination function. So, yeah. First, the word option. The word option is just another word that we, it's like an action, but it's not an action because it's a higher level thing. And it is this pair. So the policy, we know what a policy means. It means some map from states cross actions to probability of taking that action in that state. That's just a policy of the option. And the termination condition is the familiar termination condition. It's the probability of it actually it's not terminating because gamma means that's the probability that we continue on in each state. And so the idea is that when you choose an option, you start following the option's policy, and then you keep going and deciding whether you're terminating it at every step according to gamma for the option. And then at some point you're going to terminate, and that'll be the end of the option. So you're going to call it, you're going to run it for a while, and then till you end. So an example is I've got a robot, and he has an option for docking, and so his policy may be some built-in thing or something that some programmer like you maybe built in for him to try to dock, and you'd build in a recognizer, a termination condition, so you can recognize that I have docked. Or of course you may be trying to dock and then it may fail, like you may lose sight of the charger and you're lost going in another direction. And so these would be two ways you could terminate. Okay, so you'd like to think, oh, will this docking controller, will it work or will it not? I can ask that. If I run this thing, will it end up in this way or will it end up in that way? Okay, so that's the idea. And you also might have options for like going to class, right, which ends up with your being here and terminates when you arrive here. You might have an option for opening the door, or for going to the restroom, or whatever you want. Adam.
Is it an accident that this termination or continuing thing is called gamma?
Yeah. So you don't want to. Well, I'll tell you. The first time we read it, and we made it, and I guess you read the paper, the options paper, and we call it beta. Okay. But beta is exactly 1 minus gamma. Okay, it's like the probability of there's an inversion here, right? Gamma is always continuing, beta would be not terminating, but it is sort of very similar to the discount. Discount is like it's like you're always terminating a little bit on each step. But still, these are separate ideas. The discount, remember, is a measure of Anyway, we're going to have both of them. We're going to have both discounting and we're going to have termination. A common case is that you would terminate just the way we have discounting, with a constant termination, a constant gamma zero. So that, like, you have a robot and you say, well, what if I just start moving around randomly? Am I going to bump into something? Well, you can't ask that because eventually you will always bump into something. But you could say, will it bump into something soon? And a good way to say that is just terminate with probability 1 minus gamma, and it'll be like, what's my probability of running into something soon? And a discounting measure, discounting-like measure would be like that. So discounting is a form of termination, and I hope that's a good enough answer. Okay, any other questions? You want to think about big behaviors and reason about them with the same technology we've had so far. The technologies, so they're like actions. We'll have just like we've always had a set of actions available in each state, we'll have a set of options that are available in each state. We'll call it big O, fancy O. And you can have a policy over, just as we could have a policy over actions, we can have a hierarchical policy over options. So in each state, you pick an option, and then you follow it until it's done. And then in the new state you find yourself in, S prime, you pick your new option. Okay, so we'll have H. I call it H instead of pi. H of O given S gives us a hierarchical policy. And the key, this is true, but not essential right now. But notice that actions are a special case of options. An action is an option that ends in one step and always picks that action. Okay, so they're like that, and we're retaining all our machinery. So the value functions are going to be pretty straightforward. A value function given a hierarchical policy is just like a value function for any other policy. We have discounting is here. So we can say how much reward we will get while following the option until it's, yeah, this would be a hierarchical, this is not an option, this is a hierarchical policy. So the policies for the value function for hierarchical policies are the same. But let's now, if we go, what about, these are analogous to V pi and Q pi. But what about the starred version? What about the optimal policies? Now we can do something a little bit different because we might have only a limited set of options. A set of options, remember the options could include the primitive actions, but let's say we don't have all the primitive actions. We only have a limited set of options. So then we can define a new value function, a new kind of V star that's conditional on the set of options. Okay, this is how good it is to be in this state, and the best you can do from that state if you only pick from this limited set of options. Okay, and similarly for the action value function. So this is the first somewhat magical thing we can do if we have choices. We can define these value functions. Well, let me just give an example. I think I'll have an example coming up. Well, first a little bit of intuition. Markov decision process, we just have these little clicks. We go from state to state. There's something called a semi-Markov decision process, which lets you make big steps. And the special thing which we have options is we have a little MVP, but we also can make these big steps. We can jump from one thing to the next. Okay, and so that's sort of we have a jumpy MDP overlaid on a primitive MDP. Okay, so I guess the last formal step, I need to generalize models. You remember the model? The model of an MDP gives us, we generally had a 4-argument P function, which gives us the probability of a next state and a reward. But as we discussed early in the book, you can break that down into these 2 parts, and it's more convenient to use these 2 parts at this point. So one part is the reward part, gives us the expected value of the 1-step immediate reward given the state in the action, and this is the expected next state given the state in the action. So these are this is the usual thing, and now the option generalization is that you have now for a state and an option, you have not the immediate reward, but the immediate reward for several steps up until the option is done. So this is the reward along the way while doing the option until it ends. K here is the imagined time, is the time looking into the future. It's a random variable when the option terminates. So K is determined by your termination function, gamma. Okay, so instead of having the 1-step reward, we have the K-step reward, or the total. It's not K, some definite K. It's however much total reward you'll get before the option ends. And the transition function is a little bit more scary. It's basically, we have to consider all the Ks, all the possible number of time steps it might last. So suppose it lasts 2, and you have the probability that you're going to be in S prime at t plus 2, and you terminate at that time. Okay? So all the different possible times you might terminate, And what would be the state, what probably you end up in state S prime. But then at the end, it's all going to be gamma. It's going to be, this is regular gamma, not gamma 0. This is, remember, this is not gamma 0 either. This is the actual normal termination, normal discounting. So we're basically saying, how likely am I to end up in various states S prime, taking into account how long it took me to get there. So if I don't get to a state for several steps, then gamma to the k will be small, and it'll be discounted away. So this transition probability is not really a transition probability. It's like a transition probability, but it has the discounting mixed into it, and we have to do it in that way. But once we have done it in that way, we form models of this form, then everything works just as we have done it before. In particular, the Bellman equations. I think that's next. The Bellman equations. These things should look just like our familiar Bellman equations. And remember, I told you always think about Bellman equations. Think of the backup diagram first. So here we're imagining we're at a state. We're following a hierarchical policy. So we're going to pick one of these options. And we look at the reward. RSO tells us how much reward we would get for picking that option in that state. And then this transition quote probability will tell us about the states we might get to. It's the same picture, except instead of having pi and a here, we have the choice of options according to the hierarchical policy. Okay, and here now we're going to sum over our possible things corresponding to this branch, and the reward we get plus the value of the next state according to how probable that next state is. Now, the only thing that's different here from our traditional Bellman equations is, well, it's a little bit different because we have the R and the P, three argument P version, but that part is really the same. The only thing that's really different is there's no gamma here. There's no gamma because these are transition probabilities that include the discounting within them. So in particular, the one-step form of this, because if your option was a primitive action, just took one step, this would be the transition probability times gamma. So it's already in the P. Okay, so and this also the action value form is the same thing. It's really it's beautiful because we're writing the same Bellman equations, but now we're not talking about suppose I could do this little action. It says suppose I do this big choice, like what if I go to the restroom now, or what if I take the airplane to Toronto? We can think about all these larger problems in terms of the machinery that we've already developed. That's the whole thing. Okay, so planning methods based on the Bellman equations, we would do something like value iteration, which we talked about all the way back in chapter 4. We have some array, we initialize it somehow, and then we do the Bellman equation over and over again. Okay, and then our approximation in the array will converge to V star. And once we have V star, we can make the greedy policy, and this is in fact a strict generalization of conventional value iteration. If the set of options is only the set of available actions, then it is value iteration. And let me show you an example of how this goes. So we'll go back to grid worlds. So here's what's called the four rooms world, and we have our rooms with a certain number of states, and these hallways. Okay, so the options, we're going to give it the options. The options are policies that, well, here's an example. One of the options has a policy that brings it to this hallway. So now instead of thinking about, oh, I'm here at some point and I could go right, instead we think, well, I'm here in this state and I could go out the door. Okay, I could go out this hallway. That's the option. The option is this is its policy, and the termination function is when I get here, it ends. I think if I leave out here, it also ends. Okay, so there are actually 8 of them because there's 4 rooms, and each room has 2 options, one leading through each of the 2 hallways. Okay, option 1 and option 2. So the actual MDP, all rewards are 0, except when you reach the goal. And we're going to consider 2 cases. I think we'll start with the goal being right here on this hallway. And later we'll have the goal possibly being there. Okay? So the real problem that has a discounting, don't confuse that with the policy of the option. The option here, I think, terminates only when you reach the target or wander out the wrong door. And so that the options will have a binary termination function. They have this go following the option until you terminate by leaving the room. Okay. I guess a little bit of just subtlety is we've arranged the actions. The actions usually have the four actions usually have the usual semantics, but a third of the time, instead of, like if you pick right, then 2/3 of the time you'll go right, but 1/3 of the time you'll instead go in one of the other 3 directions. Okay, that's perfectly fine. So that's the way we've set up this world. So even if you're heading for the target, you might wander out the wrong doorway just because you're unlucky. Okay, that's the world, and that's the set of options. And let's run value iteration. Okay, so here we are with a goal, and if you just run value iteration, that's what we're showing up at the top. We have regular value iteration without temporal abstraction, and here we have the options. And so if you just do regular value iteration, you do a sweep through the whole state space, updating every state. Most states are unchanged because most states just say, oh, I'm here and I could go there, small change, and I expected nothing and I got nothing. And so there's no change. Only this state, when you go down, you'll learn that this is actually very close to getting the goal of +1. So after a whole sweep, you really only change these 2 states. And after 2 sweeps, you change their neighbors. Okay? Whereas, if you have options, and you can back up along the options, then when you, even a state here, you update him, you're going to say, well, I could follow my option would take me there. And that's good. And similarly up there. So all these states, this whole room gets filled in one sweep. And you can correctly value any of these states. There's no more computation done here than there. It's just over here, you can only think one step ahead, and nothing really gets you anywhere. Here, you think one step ahead, you say, I get to the door. I get to the hallway's good, I'm good. After 2 iterations, the first iteration you figured out that this is good, and this is good. And so now all of these can get you here. And so in the second iteration, you can fill in the whole space. Planning is dramatically faster. That's the big win. Okay, think about that. Let me give you the other example, because you may think, oh, this is kind of a setup, because the goal is right on this hallway state, which is where the options take you. The options don't take you to the other states. What if the goal is here, the second location? So I want to do that second location, and here we have just the case with options. So if we're doing value iteration with options, and this is a case. The set of available options are our 8 options, but they're also the 4 primitive actions, because none of the options take you to the state, and if they alone were available, you wouldn't learn you wouldn't plan anything. On the first sweep, you learn the neighbors of the goal state and nothing else, or you update the neighbors of the goal state and nothing else. On the second sweep, it gets a little bit bigger, but still If you plan here, the only thing you can learn is the guys that lead you into one of these states you know are good, are non-zero. But now you finally reached the hallway, okay? And now you can fill in the whole room, okay? And then you can fill in the other rooms. So it still gives you a big speed up. Okay, so you understand what's going on? We'll do a little test to see if you understand. I'll ask you a specific question. The specific question really is about to explain this point. Because if you look back, from here to here, we're just adding all the neighbors of the green points. So here, this is a neighbor, that's a neighbor, but this corner thing is not a neighbor. There's no way you can go from him to a green. So the question is why, but he is filled in. He's filled in, and also this one is filled in, even though they're not immediate neighbors of the places you know are good. So why is this place filled in? All of these three, I guess, are all unclear why those would get non-zero if we were just spreading out one sweep from this set. Okay? Does anyone have an idea? Just one guy? Well, then you better ask some more questions. I don't want to give it away if there's only one guy. He's got it. Give me a chance to put on my glasses. You guys think about it some more. Why is that filled in on that's fourth sweep? Sweep. Maybe there were more people that raised their hands. I just didn't see them. Okay, the questions you might ask me. We're backing up from using our model. So why is it that we can fill in a whole room? Here on this sweep, we fill in this whole room. And it's because on this sweep, we found a non-zero value for this hallway. And we have options, an option model. There's options and there's option models. The option just says what to do. The model says what will be the consequence of doing that. Well, the option is actually a relatively small thing, and the option model is a larger thing. Just like actions are tiny things, and yet the model of an action, has got to be big. It's got to say, if you do that action in each state, what would result? Okay, so the model of the option that I described to you as going to this hallway, it says how much will I be discounted by the time I reach there? And so for each one of these, it can say, I'll be discounted by some number, and then this has a value represented by the size of the dot, and so I can move that to here. This guy's saying, oh, my primitive actions don't lead me anywhere, but I have a big option that will lead me here, and I'm updating according to the max, synchronous value iteration, and so all of these get filled in one step. Okay? So why is this filled in? Okay, now that remember people are raising your hands, we can. Do you still have a reason?
Yeah, because we have a value at the doorway, so that you can use the option that
We have a value at the doorway. The man says this doorway. And so the fact that we're filling in this guy, it represents what policy? Or what plan?
The options we get from that.
It's sort of saying, what if I go from here to there? I could jump that, and I know this is good because I know how to get back from there to here. This is not a great plan, right? Because it's an indirect thing. It's sort of saying going dunk, dunk. And so you can see that because after another sweep, it's found the shorter. This thing grows from here to this larger thing. That's representing the shorter plan of just going directly. This is the long plan. Okay? Yeah, and similarly for this, the long plan of going there and then down. And after another sweep, all these get larger. So yeah, we do this all the time. You say, okay, I could get some milk. And how do I know I can get some milk? Because I know how long it takes to get to the bank, and the bank is close to the grocery store. Okay? And but the grocery store may actually be closer than the bank. But your theory says, I could just go to the bank, and then it wouldn't be far away, and I could get to the grocery store. Okay? But in fact, you don't really want to go to the bank and then come back to the grocery store. And if you started walking towards the bank, you'd say, well, there's the grocery store. I'll just go to the grocery store, and I won't bother going to the bank and coming back. So this is what I would call interruption. You have a plan, like I'll go to the bank, and then I'll come back to the grocery store. But if you realize you can interrupt your policy along the way, very sensible thing to do, and you can do better in general by doing that. And I'll show you some examples of that. Okay, but first here's a summary graph. It shows how fast, actually instead of doing planning, we're doing learning now. We're learning in the normal way with grid worlds. We would do, you travel along paths and you do like Q learning on the steps. And if you do Q learning in the normal way with actions, you learn, but it takes you a while. Notice this is a log scale, a little bit compressed out here. So this is it takes you, maybe 50, 30 or 20 or 50 steps to find the right thing. Whereas if you can do options, you can very quickly, this is a number of episodes, it takes like 50 episodes. You could very quickly find it. And the best is if you don't have any actions at all, if you just have theories about options. Okay, so,
One question.
yeah, good.
So if you're just using options, how do we make sure that we end up at a spot which is not the doorway?
Yeah, so you couldn't do that for the second goal location. But these results are for the first goal location. So it's okay. Yeah. You need to have both. Also, while we're mentioning that, how many actions are there? How many options are there? There's 4 actions, and there's sort of eight options. But really, in every state, there are only 2 options available, right? In a room, you can go to one door or the other door. And so there's really only 2. And so if you have options only, it's actually cheaper. The planning process is cheaper per sweep because you're only considering 2 possibilities. And if you consider them both, you're still only doing 6 possibilities from each state. So it's a little bit more expensive than regular planning or regular Q learning because you have a few more choices. Good. Thanks for the question. So the theory comes from semi-MDPs. A lot of things comes from that. But the most interesting issues are these sort of mixing, I have a plan that involves these jumps, but I might not follow that plan. I might interrupt the plan. Okay, so I wanted to try to cover some of those things. That's the most interesting things are when you have these mixing things. And so the first thing is this idea of interruption, that I might follow the plan, but interrupt it. Okay, so when you interrupt your plan, basically, is if you're heading for the bank, and then you notice along the way it'd be cheaper just to go straight to the grocery store. Okay, and so that is a very particular condition that you can check as you move along. You're in some state T, and you say, well, how good would it be if I kept going with my plan, boy, what is this? If you get a better in this state that you're in now to reapply the hierarchical policy to this new state, as opposed to keep following the option that you selected. Okay, and if that's the case, then you want to switch. Okay, let me just show some examples of this. So here's a problem where I have a continuous state space, continuous two-dimensional state space, and I have options that apply within limited regions. So anywhere within this green oval, green circle, I can choose to head towards this point in the two space. Okay, these blue lines represent the option of heading there. Like I have a plan, if something is close enough, I can see it, and within the horizon I can see it, I can just head towards it. Okay, but if I can't see it, I can't head towards it. So those are the options, and whereas the primitive actions are like tiny, they're like maybe 100 steps to go from here to there. Okay, so I don't really want to plan at those primitive steps. I want to plan at my big steps, but right where I am, the only, if you see the circles, the only thing that's within my sight is this one. So I can't go for that one because it's too far away. I can't see it. But I can go towards this one, and then as I head towards it, I'll come with that one will come within sight, and so I would have the option of I can either keep going with the option that I've chosen, or I could switch to the new thing that's within sight. And so if you just plan with the options, you will end up learning, well, maybe it's the next slide. If you just plan with the options, you will learn this solution that says, oh, go to this one, and then go to that one, and do the square policy that has a certain distance. Okay, but if you can interrupt your options, you'll go to here, then you'll say, oh, I could choose that one, you'll head for that one. But before you get there, here you'll have another one will come within sight, and you'll head for it. And so you end up this more direct green route. If you can interrupt your options, you can do better. And you get a higher value policy. And there's no real cost, because the cost was computing the value function for the red policy, and then just using that existing value function, you interrupt. You say, I could go that way. That would be cheaper, and I'll do it. Okay, so let me show you a video of what this lets you do. So the video uses what I call the spy plane example. And the spy plane, there's our spy plane up there. He starts at the base with a certain amount of fuel, and then he wants to go out there and take photographs of these various sites. Okay, and he gets different amounts of reward. If he takes a picture of this site, he gets 15 units of reward, whereas if he takes a picture of this site, he only gets 5 units of reward. And complicating the problem is there could be weather. You could fly there to take a picture, and it's cloudy, you can't take a picture. Okay, so here's a cloudy city. It's worth a lot of points, but if you fly there and it's cloudy, it doesn't do you any good. The only way you can get points is to be there when it's clear. Okay, and these other blue numbers are like how the clouds, the statistics of the clouds, how often the clouds, how often that site is cloudy, how often it's clear, or how often it switches from cloudy to clear, and vice versa. Okay, so that's the problem. So an individual motion, it's 100 steps, I think, to go from the base, say, to that most valuable city. So it's 100 steps, and you could not plan at the base level. It would just take you the state space would be too large. Yeah, 100 steps to go from here to there, and so that's the problem. And if that's not clear, a video demo always makes it more clear. And let's just skip to the video demo, and then we could come back to this. Okay, so I don't know if you can see. This is a bar. It's going to get our fuel, and this is our base. Those are our cities. This little white thing is our airplane. And so we fly from city to city. And if it's covered by red, it doesn't do you any good to be there. You can't take a picture. No score for it. But you have to get back to the base before you run out of fuel. Okay? And that sound is when you are successfully taking a picture, and then the color of the 25 turns bright. So you get to so he didn't see, he really wants to get that. Yeah, there, it's good. Okay? And he has to give up on those guys. Sometimes you can get them all. No problem.
Does the plane run out of fuel and get stuck, or does it automatically go back?
He has to decide to go back, just like he has. So think about the decision. The decision it makes is which option to do. It's got an option for each one of the 5 cities and for the base station. And it's only deciding which option to pursue. Even though, the decisions, the big decisions are only which one of those sites to head for. But it does have little decisions at each moment by moment. It has to decide which one to head. So you see it kind of headed one way, and then this place got clear. And so it's making moment by moment choices depending upon you can tell he knows if a place is cloudy or clear. But he doesn't know if it'll be cloudy or clear when he gets there. You see, as always, you can see that it is really a moment-by-moment choice, depending upon the weather report. So what you're seeing is after planning. He planned at the level of big choices, and now he's acting at the level of the little choices and doing interruption. So he's not actually learning now. He's reading out his plan. The plan says when to head for each place, when to give up on a place, and when to head back to base. So I like this demo because it shows, high-level decisions being made in order to maximize the objective. Any questions? Yes.
So does the agent have to learn when to interrupt also? Or is,
And every time step, it's deciding whether to keep going or to pick one of the other choices.
Are options always predefined, or can they also be learned?
No, we would like to have them be learned, but state of the art is to have them predefined. Just similar to like features. Features, we would like features to be learned, but state of the art is to have them. That's not true. We could use deep learning. That's got magic in it. That'll always work. Yeah, we would like to learn the options. Any other questions? Adam.
were you working for the government when you came up with this problem?
I hate the government. I would not take military funding anymore. My first funding was all from the Air Force, and this made sense to them. I don't think they ever used it, though. That's good. Yeah, don't study war. That's my advice. Okay, good. Yep.
Do we generalize well when we use function approximation?
Excuse me?
So what happens when we use function approximation?
Yeah, all the examples you'll see about options, and you read the options paper, are all for table lookup. And the ideas are totally general. That's another dimension to add function approximation. And it all works pretty well, except for something we haven't explicitly covered in class, but you might have noticed. You know, we went function approximation up to the on policy control. We didn't do off policy control. Off policy control is harder. The off policy with function approximation is hard, and I think now, 18 years later, we know how to do off policy learning with function approximation pretty well, and that's what's needed. You need to be able to learn off policy in order to learn. You know, you'd like to be able to like move however you move and learn about how the models for getting to all these places. And so you'd have to learn. You have many things to learn, and it's an off policy problem to learn the option models. And so the examples are all for table lookup where off policy things work. Yeah. Okay, good. Yeah.
So, one question is...
Hey, Mohammed, it's good to see you.
So, the options in this example are
Yeah.
to go to the spots,
Yeah.
do survey. So, there might be some other options which are also useful, which are not put in this program.
They're not available.
They're not available. For example, to go to a place just in the middle
Yeah.
of two different places. Like
Yeah.
two different photos.
Yeah. Look, did you see that? Sometimes it goes like, it's like it keeps changing its mind. Go one way and then go the other way, and it kind of goes in between.
Yeah.
But you know, it's quite likely in any application you're doing that, yeah, the choice of your options is critical to getting really good policies. And you know, you may run something like this, and the options aren't good for your problem, and so you might have to add some more options, or have some automated procedure for discovering them. Yeah, I think that's like a really exciting thing for the cutting edge today, is to discover the options, search for the options. Yeah. Okay, so the rest of the thing is just me celebrating. The mission is to fly over. The weather is stochastic at limited fuel. This is intractable with classical methods because of the timescales. And you can reduce the complexity. Instead of having a search depth of 600 steps to go to fly a mission, you'd have like 6 steps to fly a mission. And so that reduces the state space by a huge order by several orders of magnitude, 4 orders of magnitude, and then makes it tractable even back then when this work was done. Okay, and here we show results for the cases. If you did, what do we have here? What's expected reward per mission, and if you do a static replanner, so what does that mean? SMDP, assume weather will not change. So we see here, we can see the weather how it is now, and we say, let's make an optimal plan, assuming that it stays the way it is now. You can do that. It's like a traveling salesman thing, and but you're not going to do very well because the world does change. The weather does change. And if you assume the weather does not change, you're going to get a poor plan. If you do the proper thing, but always plan SMDP, and you mean always follow the options to all the way to the place you're heading for, even if it turns cloudy, then you can't do as well either. The best thing to do is a pretty good thing to do is to plan as if you're going to all the way to the end, but actually redecide on every step with interruption. Okay, and so that's that. And I just want to give a taste of a couple other things. We got good time. So what's this? This is intra-option learning methods for Markov options. Okay, so how does this learning happen? The most obvious way to learn is what are we learning? Actually, in this problem with the airplane, what do we learn? Okay, we learn. We have the option. So the option, for example, this option tells me I I can follow this policy, which takes me directly straight towards this city, this site. Okay? And but the model of the option tells me what? What would the model of that option tell me? Well, there's a reward part and a transition part. The reward part is it'll tell you what's the expected reward for going there, okay, which would there'd be 0 reward along the way, and then 25 when you get there if it's not cloudy, okay? So it will tell you the expected reward, how likely it is to be not cloudy there, times 25. That would be the model of that option, okay? In terms of the reward. Now, in terms of the transition probability, what are the states? The states are something like they're exactly which cities have been visited, and are they cloudy or not? Okay, so the state is which of these 5 cities have been visited, and are they cloudy? Okay, so it has to reason things like, if I go there, I have some probability of getting reward, and I'll then be in a, even though this guy is, for example, clear now, if I go here, by the time I get here, he may be cloudy. So it'll give me the probability that he's cloudy. It'll give me the probability that this guy has become clear, and so forth. So given the state, in terms of which sites are clear, and the state doesn't have to say where you are, because you could be anywhere in this whole space. But this option always takes you so that you end here. So the fact that the option takes you all the way to the site is critical for you being able to form a simple model of it. Even though when we actually use this, the results of planning, we won't necessarily go all the way to the end. Okay, so those are the option models. And you'd like to be able to fly around and learn about all the options as you behave. Okay, so that's what we want to do with inter-option learning. We don't just want to fly all the way to the place and see, oh, it took me, I flew there and it was clear. Because you don't always want to fly all the way there. That's wasteful, because maybe you got there and as you got close, it's clearly there's bad weather. You don't want to go all the way to the end. And so you have to be able to learn when you haven't fully executed the option, when you've only partially executed the option. And if you only partially execute the option, then you can't do on-policy learning, because you're not following the option's policy. You're deviating from the option's policy. And yet you still should be able to learn a lot. Like I was heading towards that site, and it was all cloudy, and so I decided not to finish and go all the way there, but it was clearly it was turning out bad. It was turning out that it was cloudy and it was not working well, and so I should be able to learn from that. If you really were doing on-policy learning, you wouldn't be able to learn from it. So if you carry these ideas to the extreme, you want to learn on every step. After each primitive action, you don't jump to the end of the option and then learn. You learn after each step using TD-like things. Like you might think it's going to be clear when you get there, and now you're halfway there, and now you think it's going to be cloudy when you get there, so you decide not to, but you still learn from that. Okay? So in the end, I don't want to go through all this in detail, but you want to learn on each step as if you were going to continue with the option, but you might actually do something else. And you want to be able to learn from that. And it follows really from all the things you've learned in class, how to do step-by-step TD learning, but it is going to be off-policy learning. And there'll be an algorithm that's just like Q learning. Q learning is an off-policy algorithm, and it'll work fine for the tabular case. So there will be tabular algorithms that work all just fine for this case. And we have results for some of those Q learning-like algorithms here in the rooms world. Here we are learning the value of a policy. We're inter-option. We are learning on each step the value function. And you can see here we have two states that have two different true values, and those true values, their option values are converging where they should. So here we're learning you're not actually ever following the options to completion. You're only taking individual steps, and yet you're learning the values of following those options. Okay, because you can learn off policy. And you couldn't learn with an SMDP method, because SMDP methods are based on going all the way to the end and then learning according to that big step. You're going to learn from the little steps what the outcomes of the big steps would be. And here we have the same thing where we're trying to learn the models and compare various methods. If we can learn with intra-option learning methods, we have the best learning curve. Whereas, what are these two cases? Oh, this is just two. Reward prediction error, state prediction error. I think these are just for two states, just like on the previous slide it had two states. And we're learning about their values. Or learning about their models in this case. And in both cases, the intra-option methods can be much faster. So if we could learn off policy, we get superior performance. We really want to learn off policy. That's why we spent so much time in the book with off policy learning. Okay. Okay, so a couple other observations. Sub-goals. It's naturally for us all to think about sub-goals. And now, so far we haven't been able to learn really about sub-goals. We've learned, we learned a value function. The value function might give you a big reward for taking the other guy's queen, okay? But really it's just saying, oh, it's good to have a queen because if you have a queen, you're probably going to win. Okay? It isn't really learning about how to take the guy's queen. Okay? But now with options, we can have the sub-goal of achieving getting to the door quickly, or juggling well, or sitting down, a really good job sitting down. And you can do the thing like, I did a really good job sitting down, but maybe it was bad to sit down. Okay, we distinguish between I did a good job at this sub-goal, but maybe the sub-goal was a poor choice, was a poor option to execute. Okay, so now we can separate it, because learning the models is like learning the sub-goals. Is learning the outcomes of that way of behaving, an efficient way to sit down. So what I pointed out here is that it's actually, we can talk about this precisely. We can talk about, we have to assign sub-goal. So the setup here is we can decide that reaching the hallway, this hallway state, gets us an internal reward of 10 in one case, or maybe gives us a reward of 1 in another case. Now these are not rewards, excuse me, these are not rewards in the sense of full rewards, they are sub-goal rewards. So what do I mean by that? I mean we assign sub-goal rewards, and then we learn the option that maximizes those sub-goal rewards. The option will ignore the true reward. We'll just look at these sub-goals. So we get to create, we say, suppose it was good for me to get out this door. Suppose it was worth plus 10 to get out the door. And they will learn a policy appropriate for that. Now the policy that it learns would be different if you said it was only plus 1 for getting out the door. Or at least it could be. And this is a setup where it is different because there are small rewards on each transition in here. And in this case, going to the right, say from this state, would actually be a slight negative reward. And so it's chosen to instead, well, that's kind of crazy. It would just go back and forth. I can't explain that one. But okay, it really all kind of seems crazy, but oh no, this is possible. Like it may be that with the random rewards, the right thing to do, like from here, is to go to the door, but from here it's better to just stay over here and not go to the door, because it's only worth plus 1 to get the door. It's not worth going through the badness that you have to go through. That's perfectly possible. So it's like you might have a sub-goal for getting into your car or getting into your house, okay? And it would tell you how to open the door and so forth. But what if the door is locked, right? If your goal was to get in the house, you would break down the door, okay? And so you might never be able to use this option, because if by chance the room was was locked and you didn't have the key, you'd have to break down the door. So this would be a really costly option. It would force you to break down the door. So instead, you might want to have the option of opening the door if you don't have to break anything, okay? But if it's too costly, you don't do it. It'd be potentially a much more useful option that you could actually consider in various plans. That's probably what we do. So I could walk home and then I could go in and get a glass of orange juice, and because I can just walk in the door or unlock the door. But if I do walk home, and I mean, if it's locked, then I do something else. Okay, you have to be able to form that policy. And so anyway, you have sub goals, and they determine your options, and then you learn models of your options. And so we can this gives us a way to answer the problem that Mohammed brought up and that some of you brought up of where do the options come from. You don't have to give whole policies. You could give sub-goals. The sub-goal for sitting down and the sub-goal for going out the door, and then you can learn the policies that produce those sub-goals. Okay, we still have to give sub-goals. Some guys still have to say, oh, it's getting out the door was important, sitting down was important. They don't have to give the whole policy. And we can separate the skilled way in which you sat down or opened the door. We can separate it from the decision of whether it was a good idea to sit down or a good idea to open the door. Okay, so we're done. What have we won? What have we benefited from options? One is we get transfer of knowledge. We can learn about sitting down and then get really good at sitting down or opening the door or going to this place or that place. And then we can transfer that to a new problem. We can think about, I can combine these big steps, and so we're basically reusing the solutions to the subtasks because we have a place to save them. We're saving them in the models of the options, and they are stable and safe there. If we decide not to use an option, we still know the option, we still know its value function. We've just chosen not to use it and follow it. And so this can give us much faster learning and planning, so that we can do our planning in an appropriate temporal scale. Models of options are a form of knowledge representation. We're going to capture important knowledge: how to sit down, how to walk, how to go from one place to another. This is knowledge. What do you want in a knowledge representation language? You want it to be able to express anything. You want to be able to talk about objects in space and sitting down. You want to be able to think about large steps, traveling to Toronto. You want it to be clear. You want it to be mathematically clear. And you want it to be suitable for learning and for planning. And I'm thinking that really option models give us all of these three things. They're just designed to fit into value iteration in the Bellman equation, so we can use it for planning and for learning. They're mathematically clear in their semantics, and the expressive perhaps is the one that needs the most argument. It needs the most support, and it's harder to assess. Is this an expressive language? Does it capture? Is any form of world knowledge that we might be interested in? Is it expressible as an option model? Sort of the argument for it is that it's kind of like scientific knowledge. An option model is, what if I perform this experiment? What would be the outcome? Performing the experiment is the policy, and every experiment has to terminate. And it terminates with some measurable thing like a reward or a state that you've reached, and so I think we formed this hypothesis that they are sufficiently expressive, and we're still testing that out. Okay, so it also gives us something to do with our big brains. We're not just learning a policy and a value function, which is just like two vectors. Instead, we have to learn this whole model of the world. Because there are infinite number of options, and we're going to learn many, many things, and we have to construct the correct options, or options that are useful. We'll continually be learning, continually be saying, oh, is this option being useful or not? I have millions of options, and because my brain is big, but still my brain isn't that big, and maybe half of those million are not very useful, and I throw them away and consider some others. And so I'm always developing a better and better way to understand the world, and both in terms of accuracy and utility for rapid planning. Okay, in conclusion, just this one trick of having options really takes us a long way towards linking human level, high level choices to the microscopic little actions that we pick all the time. We can represent temporal abstract facts about the outcomes of different ways of behaving, which gets us close to the idea of knowledge. And we have a theory of how to combine the subcontrollers for achieving these things. And so now I think we can go even beyond saying the beginnings. We have pretty good ideas about how to learn them efficiently online. And so the high level can mirror the low level view. Everything is choices and states and values. This is sort of in some sense, we've got towards high level ideas, and yet we've minimally extended these low level things about Markov decision processes. Of course, we're still relying on state, and all through the book we've relied on state, and but I want to say a little more than acknowledge that limitation, which is that the notion of options may provide some traction on state, because so what is a chair? A chair is something like a set of situations where my policy, my option for trying to sit down is going to work, right? If you're stuck somewhere, I don't know, in the forest or something, there may be no chair, and one way of describing that is this option for trying to sit down, it says it will fail. So so you'd characterize the states you might be in. Those states in which I can sit, those states which I cannot sit. This is like those states in which there's a chair here, those states where there's not a chair here. And similarly, with these physical objects and states, if we could characterize our current state by its options, its opportunities for action, which are the success of the various options. This is a place where I can throw an object. This is a state where I can press the clicker and get the slide to move. This is a state where there's chairs. This is a state where I can talk to various people. This is a state where I can put something here and have it supported on its own, and lean on this table, the flat surface. If we write down all those facts as predictions about the outcomes, it gives us a higher level representation of the state in terms of opportunities for action and their possible outcomes. So I think options are also going to be key to getting a better, more useful notion of state and how we perceive the world. Okay. Any questions? So as I said, it takes a little bit of while to absorb all this. I'm sort of saying all the stuff you already know is bigger and more generally relevant than you might guess. So maybe I'm saying it's a small thing to learn, but really to absorb that message takes a while. Because I really want to use it to capture all that we know about the world, all common sense knowledge. We couldn't represent it as MDPs. That'd be too small. But maybe we can represent it as option models. And it's sort of minimalist. We haven't had to add, well, we had to add options and then option models. We haven't had to add, I don't know, language, or haven't had to add space, haven't had to add ideas of supervised learning, autoencoders, haven't had to add ideas of compression. We've got abstraction just through time and the dynamics of the world, and by being willing to devote parts of our brain to learn more and more things. And this gives us a major, I think it's a major path towards abstraction, maybe almost all we need. Adam.
Can you talk a little bit more about what do you mean by temporal abstraction?
Temporal abstraction, temporal, as you know, is just time, just like in temporal difference methods. So what does that, we use this word abstraction. Usually it's just informally, but I would say that there are two kinds of abstraction. There's time abstraction and there's, now you may be tempted to say space, time and space, but I don't think space is fundamental. State is fundamental. So I'd say there's two kinds of abstraction, time and state. So state abstraction is we say, oh, function approximation. I'm going to treat all these states as if they're similar. So function approximation is really state abstraction. Temporal abstraction is where it lets us capture ideas that last more than one time step. So an option, when I say, if I try to go up to that corner and go out the exit door, the door will be open. I'll be able to open the door. Or I could say, no, I think it'll be locked. If I push on it, nothing will come out of it. Okay, so that's a statement about many steps into the future, because it would take me a few seconds to get up there. So many decision steps. So I'm abstracting over time. Temporal abstraction. I think temporal abstraction may also be the key to state abstraction. As I talked about, this is a state in which I can sit on the table. I can rest here without falling down. Okay? So I have this idea about table, and sittable is a long-term, a slightly long-term thing. Yeah, if we can do abstraction in state and time, then we're good. Okay, any other comments? Yeah. Okay. Okay. Thank you very much.